Now let us look at the last method called hold equivalence or zero order hold equivalence. So we want to design a discrete system that, given an input of samples E of t, has an output that approximates that of a continuous system with an input of a continuous E of t. So basically what a zero order hold does is holding E of t constant at E of k over the interval from kt to k plus 1t. So that's what a zero order hold does. So for example, if you have samples, if you take samples like this, at various values of k, then what a zero order hold will do is, if you go to first k, the value at k, it will hold it up till the next sampling time until we go to k plus 1. And then the value at k plus 1, it will hold it up till we go to k plus 2, and then so on. The value at k plus 2, it will hold up to the next sampling period. So what we will get is like kind of like a step function or something similar to this. So that's what a zero order hold does. And if you look at figure 5.4, part A is a continuous transfer function. So you have input E and output U, and the transfer function is h of s. Let's say this is a controller transfer function, and the block diagram in part B is an equivalent system by using a zero order hold or a hold circuit. So basically you have input E of t, then you have a sampler which samples E at a specific samples k or sampling times kt, and then the hold, like a zero order hold, will hold the value constant up till the next sampling time, and after the hold we get E bar or E hat, and that is fed into the transfer function, and from that we get U bar of t, which is the output. So this is again like it's like the values are held to these k values, and finally after the sampler we get uk. So this part from the hold, including the transfer function of the controller and the output sampler, that part is what we are trying to model in this case. So if instead of a zero order hold, if you have a first order hold, so zero order hold holds the value constant. If you have a first order hold, then it holds the value by using a linear equation. So instead of holding the value constant, it will use some kind of a linear equation like this and hold the value maybe something like this, in this way, or something like this. So this is a linear, it will be a linear equation. So that's a first order linear function there between the samples. So the zero order hold equivalent of h of s is given by this equation. H sub small h and 0 of z is equal to 1 minus z inverse times z of, so z transform of h of s over s. So this is the general equation. So properties of this method include, if h of s is stable, then h of z will also be stable. H of z does not preserve the impulse or the frequency response of h of s. So these are the properties. We have looked at an example of this in the last section, section 4, but let me show you that example again, how we can use this zero order Howell equation to arrive at h of z. So the zero order Howell equation is given as g of z is equals to 1 minus z inverse times z transform of g of s over s. So example, let's say g of s is given as the same function as in the previous case, a over s plus a. So how can we use this zero order Howell equation to transform g of s into g of z? So the first thing we need to do is do g of s over s and then do a z transform of that. But before doing a z transform, we need to convert it into inverse Laplace. So gs over s, g of s over s will be a over s into s plus a. And if we expand that using partial fractions, then you will get 1 over s minus 1 over s plus a. And if you do Laplace inverse of g of s over s, you will get, so 1 over s will be just the function 1, so 1 of t minus 1 over s plus a will become e to the power minus a t times 1 of t. So that's what we'll get when we do Laplace inverse of gs over s. Now we can do z transform of gs over s. So if we take this, and if we take, let's say, instead of t, the samples of t, so basically instead of t we'll have kt, so we'll have 1 of kt minus e to the power minus a k t times 1 kt, 1 of kt. So this is taking a discrete version of the continuous function there. So if we do if we do z transform of this function, we will get, for the first one we'll get z over z minus 1 minus the second one we will get z over, so you can refer to the z transform table for this, z over z minus e to the power minus a t. So this is what we'll get. Now after doing z transform of that, we need to multiply the whole thing by 1 minus z inverse. So first let's simplify this. So when we simplify this, we get z into 1 minus e to the power minus a t divided by z minus 1 into z minus e to the power minus a Sorry, that should be capital T. Right. Now we can say g of z is equal to so if we multiply this by 1 minus z inverse, same as multiplying it by z minus 1 divided by z. So multiply that with this, which is z into 1 minus e to the power minus at divided by z minus 1 into z minus e to the power minus at. And then after we do that, we get, after we simplify, what we get is 1 minus e to the power minus at divided by z minus e to the power minus at. So this is my final answer for g of z. So my g of s is this, and using the zero order hold technique, I got g of z as this, which is similar to what I got using matching method, matching poles and zeros.